In the last video, we looked at polynomial rings over the integers, polynomial rings in one variable, and showed that it's a UFD. In fact, we also commented that the same proof shows that if R is a UFD, a polynomial ring over R in any number of variables, finite number of variables, is a UFD. And the crucial facts we used were the notions of primitive polynomials and Gauss lemma, and using that we have written any rational polynomial as a rational number times a primitive polynomial, and that allowed us to compare irreducibility over the integers and irreducibility over the rationals. And we ended with the important theorem which says Zx is a UFD. So today I am going to use those ideas to prove a very important criterion for verifying that polynomials are irreducible over integers or rationals, and it's called Eisenstein criterion. Okay, it's a very useful method to check if a given polynomial is irreducible or not. It does not always work, but it works often, and it's very useful to conclude that irreducibility here. So let me just go ahead and write the criterion first. Let f be a rational integer polynomial. Write f as an xn, an minus 1 xn minus 1, a1x plus a0. So since it's an integer polynomial, we of course know that the coefficients are integers. So now suppose that there exists a prime integer that means a prime number in Z P such that it satisfies the following conditions. P divides or does not divide, first let me say P does not divide an. So I am assuming whenever I write like this, of course remember when we write a polynomial like this, we will always assume that the leading coefficient is non-zero, because we will start with the largest degree. So an is not 0. So suppose P does not divide an, P divides an minus 1 up to a0, and also P squared does not divide a0. Okay, so this is the assumption. P divides an, P does not divide an, P divides an minus 1 through a0, P squared does not divide a0. So remember, these two conditions already imply that n is positive. So f is non-constant polynomial. Remember that we are asking for P not to divide an and P divides a0. That means an and a0 are different. That means f has at least degree 1. So it's a non-constant polynomial. So if this happens, what is the conclusion? Then we can immediately say that fx is irreducible in Qx. Then fx is irreducible in Qx. That is a conclusion of Eisenstein criterion, not that it is irreducible in Zx. However, if we also know that if f is primitive, if further f is primitive, then fx is irreducible in Zx also. Okay, so this is a good criterion to prove, so that it actually uses all the notions that we developed in the last couple of videos, and it gives us a very useful criterion. If there is a prime number satisfying some conditions with respect to the coefficients of the polynomial, we can right away conclude that it's irreducible in Qx. We cannot conclude in general that it's irreducible in Zx, but if it is primitive, it is irreducible in Zx. So I'm going to give a couple of examples before I prove this. So for example, if you take x power 3 minus 5x squared plus 10x plus 15, right? So let's take this in the polynomial ring over integer. So this is an integer polynomial. Then p equal to 5, satisfies the hypothesis of the Eisenstein criterion, right? We might even write something like this. So let me write f equals to 2x cubed minus 5x squared minus 10x plus 15. So it satisfies the hypothesis of the Eisenstein criterion because 5 does not divide 2. A3 here is 2, right? A3 is 2, A2 is minus 5, A1 is minus 10, A0 is 15. So 5 does not divide 2, 5 divides minus 5, 5 divides minus 10, 5 divides 15, and 5 squared, which is 25, does not divide 15. So we conclude that f is irreducible in Qx, right? This is the conclusion of the Eisenstein criterion. Since f is also primitive, right? Why is that? Because remember, a primitive polynomial is a positive degree polynomial with positive leading coefficient and such that GCD of all its coefficients is 1. Here the coefficients are 2, minus 5, minus 10, 15. GCD is 1, right? There is no number greater than 1 that divides all these coefficients. So f is primitive and hence f is also irreducible in Zx. See, this is a very useful criterion. As you can see, it may be very difficult in general to conclude irreducibility of polynomials. In this case, we have already just immediately concluded that it is irreducible. So similarly, we can take, for example, f as, let's say, 12x power 6 minus 10x power 5 plus, let's say, 50x power 4 minus 10x plus 60. I am just arbitrarily writing some polynomial. So again, p equal to 5 works, right? Why does it work? Because if you check 5, it divides all the coefficients other than the leading coefficient, right? P does not divide 12, but p divides 10, p divides 5 divides 10, 5 divides 50, 5 divides minus 10, 5 divides 60, 5 does not divide 12, and 25 does not divide 60. So f is irreducible in Qx. So this is okay. That's immediate conclusion of Eisenstein criterion. What about in Zx? For that you have to ask if it is a primitive polynomial. Is f primitive? It is not primitive, right? Because f can be written as 2 times, you can factor 2, 6x6 minus 5x5 plus 25x4 minus 5x plus 30, right? This is not primitive because the content is not 1. Content of f is 2, not 1. So f is not primitive. That means we don't get that f is irreducible in Zx, because clearly you can see that this gives you a factorization. 2 is an irreducible element in Zx, so f can be written as 2 times g, where g is this, right? So this is irreducible, this is irreducible. So f can be written as a product of 2 irreducible polynomials. That means it's not irreducible. Whereas this is not a valid factorization in Qx, because 2 is a unit in Qx. So this is not a valid factorization into 2 proper irreducible divisors, whereas in Zx it is. So f is irreducible in Qx, but it's not irreducible in Zx. So this gives you an example of a polynomial, integer polynomial, which is irreducible in Qx, but it's not irreducible in Zx. So now after these examples, I'm going to quickly prove the Eisenstein criterion. It's not difficult using the theory that we developed in the last few videos. It's not difficult to now show that, now prove the Eisenstein criterion. So what we are going to do is consider the natural map, ring homomorphism I should say, natural ring homomorphism phi p from Zx to Z mod Pzx. Remember, what is this ring homomorphism? It takes a polynomial and simply changes the coefficients by their residues mod p. So given we are given a fixed p, right? P is that fixed p given in the statement of Eisenstein criterion. P is a prime number, prime integer that divides all the coefficients of f other than the leading coefficient, and also p square does not divide the constant. So for that we consider this. And now, since what I am now going to do is a simple claim here. If f is reducible, remember I am trying to show that f is irreducible in Qx. If suppose it's not, that means if f is reducible in Qx, then it is reducible in Zx. So first I will prove this claim. Let me comment that in the previous video when we proved that Zx is a UFD, one of the results we proved was if f is a non-constant irreducible polynomial in Zx, that means it's an integer polynomial, and in Zx it is irreducible and it has positive degree, then it's also irreducible in Qx. In this case, f is a non-constant polynomial, so if f is irreducible in Zx, it would be irreducible in Qx. So that this claim is proved already, but I am just going to give you a direct proof so that it becomes more clear to you. Even if the previous argument was not clear, you can follow this, right? This is a more direct argument for this statement. If f is reducible in Qx, then it's reducible in Zx. Why? So write f as gh where g and h are in Qx. Remember, what is the meaning of being reducible? That means it can be written as product of two polynomial of positive degree in Qx. So both g and h are non-constants and f can be written like this. Now, because of the proposition that we did earlier, every rational polynomial can be written as its content times a primitive polynomial. Similarly, g can be written as cg0, h can be written as dh0. Right? This is not now at this point you are comfortable with this, I hope. Every rational polynomial can be written as a rational number. So c, d are in Q and g0 and h0 are primitive. Right? So I am writing gh as cg0 and dh0 respectively. So we have this. Now remember, g0, h0 is primitive. Because g0 and h0 are primitive, their product is primitive by Gauss lemma, and f is cd g0 h0. So this must be the unique expression of f into its product of its content and a primitive polynomial. So content of f is cd, but remember f is an integer polynomial that is given to us in the Eisenstein criterion. F is an integer polynomial. This means cd is in z, right? Because content is for an integer polynomial, content is an integer. Content is simply then the GCD of its coefficients. So cd is in z. That means f can be written as g0 h0, right? And remember, g0 h0 are primitive. That means by definition they are in Zx. So they are in Zx. That means here is an irreducible factorization. Here is a factorization of f. Remember, the degree of g0 and h0 are equal to degree of G and degree of H respectively, because C and D are constants. When you write G as G0, G and G0 have the same degree. So this is factorization of F in ZX. That means if we started with the factorization in QX, a priori G and H may not be integer polynomials. We may have that they are only rational polynomials. But by writing them as product of their contents and primitive polynomials and observing that the product of the contents is an integer, we can write this. So this is actually not F is equal to CD G0 H0. I should not say F is equal to G0 H0. It is CD G0 H0. So it is an irreducible factorization. It is a factorization into product of smaller degree polynomials. Hence, F is not irreducible in ZX. That means F is reducible in ZX. So now, if the conclusion of, now I am going to go back to the proof of Eisenstein criterion. If the conclusion of the Eisenstein criterion is false, then F is reducible in QX. Right? If the conclusion of the Eisenstein criterion is false, then F is reducible in QX. By the above claim, F is also reducible in ZX. Right? It is reducible in ZX. The claim is, if a polynomial is reducible in QX, then it is reducible in ZX. So it is reducible in ZX. So I am going to now write F as G times H, G and H in ZX. Now consider the image of F in by phi p that I recalled earlier. Phi p is the map from ZX to Z mod PZX. So what we have is phi p of F is phi p of GH, because GH, see F, G and H are all here, right? And F is equal to GH. So phi p is a ring homomorphism, right? So phi p F is phi p GH, which is equal to phi p G times phi p H. Now what is phi p F? F, remember I have written F as an xn plus an minus 1 xn minus 1 plus a1x plus a0. That means because phi p is a ring homomorphism, this means this is a phi p, by definition of phi p rather, this is an bar x power n, an minus 1 bar x power n minus 1, a1 bar x plus a0 bar, right? This is what phi p does. Phi p takes a polynomial and simply changes the coefficients, it does not change x. This is equal to this. But remember, this is 0, this is 0, this is 0. So this is nothing but an bar xn. Why is this? Because remember, p divides an minus 1, p divides an minus 2, and so on all the way up to p divides a1, p divides a0. This is the hypothesis. So we have this, and also p does not divide an. That means an bar is not 0. So an bar times x power n is a non-zero polynomial. So phi p F is actually just an bar x power n. But phi p F, remember, is phi p G times phi p H. So phi p n G times phi p H is an x power n. Now we have two polynomials in F Z mod PZX whose product is this. Now recall that Z mod PZX is a UFD, right? Because it's a polynomial ring over a field. In fact, it is a PID, which we don't need for now. we only need that it's a UFD, because Z mod PZ is a field, it's a UFD, so any polynomial ring in over a UFD is UFD. So it is a UFD, and you have a factorization of a monomial like this. So this is, remember, a single monomial. So phi p g and phi p h must also be monomials of the form. So what can it be? So you have some polynomial times another polynomial is, so you have product of phi p g times product of phi p h is an. An is some constant, right? An bar is some constant in the underlying ring here, which is Z mod pz. So what can they be? They can be something, a coefficient, something like bn, bi bar x power I, ci bar x power j, where I plus j is equal to n, and bi bar and ci bar are in Z mod pzx. Right? This must be the only possible factorization. This is the only possible factorization of a monomial of the form a constant times x power n, because if there is any other factorization, that means if, for example, phi pg has two terms, then in the product also you will have two terms. So there will be two terms of different degrees, whereas this is there is only one monomial here. In other words, what are the irreducible factors of, another way of saying this is irreducible factors of an x power n are, there is only one irreducible factor, namely x. Right? X power n has only one irreducible factor. You can write it as x times x times x n times. There is no other irreducible factor for an bar x power n. There is only one. That means any divisor of an bar x power n must be a power of x. So coefficients we don't care, but there will be some coefficients. So it is bi bar xi, ci bar xj. So now what does this mean? So phi pg is ai, or in my notation bi bar x power I, phi ph is ci bar x power j, cj bar x power j. So I should also write cj. So now think of what g is. Remember, f is gh. So g is some polynomial in zx. H is some polynomial in zx. When you go modulo p, only x power I survives. Hence, we can conclude that the constant term of g is 0. Similarly, the constant term of h is 0. Why is this? Because, sorry, this is not 0. I cannot say. Constant term of g bar phi pg is 0. Constant term of phi ph is 0. So what we can say is constant term of g is divisible by p. That's what I should say. Similarly, constant term of h is divisible by p. So you have you have a polynomial g. When you go modulo p, the constant term disappears, right? Because phi pg is equal to bi xi. And also I should say I is positive, j is positive, because this is a factorization that comes from the rational polynomials. So you have two polynomials with positive degree. So when you go modulo p, the constant term goes away because only x power I term survives. So the constant term of g goes away. That means it becomes 0 in z mod pz. That means it is divisible by p in z. Similarly, the constant term of h becomes 0 in z mod pz. That means it is divisible by p in z. Now, if that constant term of g is divisible by p and the constant term of h is also divisible by p, we note that constant term of f remember, is just the constant term of f, constant term of g times constant term of h. Right? When you multiply two polynomials g and h, in the product the constant term is just the constant term of g times constant term of h. Constant terms just multiply to give the constant term of the product. So constant term of f is constant term of g times constant term of h. So this is divisible by p, this is divisible by p, hence constant term of f is divisible by p squared, right? Because this is p times something, this is p times something, so the whole thing is p squared times something. So this is divisible by p squared, but this violates or contradicts the hypothesis that p does not divide a0, right? So remember, I not only assumed that p divides a n minus 1 and up to p divides a0, I also assumed that p does not divide a0. So now that gets the contradiction. So this proves that hence f is irreducible in Qx. Okay, so now this proves the first statement of the Eisenstein criterion. If f is irreducible in Qx and also primitive, if f is also primitive, content of f is, so we want to now show that f cannot be irreducible in, f has to be irreducible in Zx. So assume that f is also primitive. If f is not irreducible in Zx, that means f is reducible in Zx, then f has to be, then f can be written as some c times f0, where c is in Z and f0 is irreducible, or f0 is another polynomial in Zx, right? In other words, what I am saying is that f can't be written as a product of two non-constant integer polynomials. What we are saying is that I am writing f as c times f0, where c is in Z, f0 is in Zx, because f cannot be written as a product of two non-constant integer polynomials. Why is that? If f can be written as a product of two non-constant integer polynomials, it can also be written as a product of two non-constant rational polynomials, because any integer polynomial is a rational polynomial. So, and we assumed, or rather we already proved, that f is irreducible in Qx, right? So f cannot be written as a product of two positive degree rational polynomials, and if it is not irreducible in Zx, there is only one possible factorization of f into a product of an integer and a integer polynomial. But of course c is also not a unit. So we have f is cf0, c is not equal to 1 or c is not equal to minus 1, because it's an irreducible factorization, right? So it can be written as a product of two non-units. So c and f0 are not units. That is the meaning of not being irreducible. It can be written as product of two non-units. So f is cf0, c is neither 1 nor minus 1. That means c divides all the coefficients of f, right? Obviously, because f is c times f0, c divides all the coefficients of f. But this is not possible Why? Because f is primitive. Remember, we are given that f is primitive. That means the GCD of the coefficients of f is 1. So there cannot be any non-unit in Z that divides all the coefficients of f. So f must be irreducible in ZX also. So this completes the proof. So we first proved that f is irreducible in Qx. Then we immediately conclude that the only way that it is not irreducible in Zx is that it's a integer times a polynomial, because it cannot be written as a product of two non-constant polynomials. That's clear. Because if it can be written as a product of two non-constant integer polynomials, then it can be written as a product of two non-constant rational polynomials, violating the irreducibility in Qx. So the only possible factorization is an integer times another integer polynomial. But then that integer must divide all the coefficients of ff. But f is primitive, so that integer is 1 or minus 1. So that proves the fact that if f is a primitive polynomial, then f is also irreducible in Zx. Okay. So now let me quickly give you some examples of Eisenstein criterion to illustrate how useful it is. So I hope the proof is clear. If not, you should just, it's fairly similar to the previous videos. So you can just go back and see the video again, and hopefully it will become clear to you. So now some examples. So we already looked at some before. Just for example, I can take x power 10. Let's say 27 x power 6 plus 230. Is this irreducible in Zx or Qx? It is, because it is irreducible in Qx first, and because it's primitive, it is also irreducible in Zx, right? It's certainly primitive because the coefficient, one of the coefficients is 1, so the GCD is 1. Because p equal to 3 satisfies the required conditions, right? Because 3 divides 27, 3 divides 203, and we also want 3 does not divide, that is clear here, 1, the leading coefficient is 1, and 9 doesn't divide 230, right? So 9 does not divide 213, you can quickly check. That means p equal to 3 satisfies this. So every time you are asked to check, or you want to know if a polynomial is irreducible or not, first see if there is a prime that works. Sometimes it does not. Sometimes Eisenstein criterion does not give you the answer. In general, there is no algorithm which always works to verify a polynomial is irreducible or not. So we are just trying to learn new techniques to do it, and Eisenstein criterion is an extremely useful technique. Sometimes it might appear like initially you don't initially you might think that you can't apply Eisenstein criterion, but some small modification works to give you the answer. For example, here you take x power 5 plus 3x squared plus 2. This is a polynomial, and you want to know if it's irreducible or not. Because it's primitive, if it's irreducible in Qx, it's irreducible in Zx. So now, certainly on the face of it, no prime works, right? Because only prime that divides constant is 2, only prime that divides the coefficient of x squared is 3. So there is no prime. Right? Because 3 does not divide 2, 2 does not divide 3. So you can't work. However, let's take this as f of x. A small trick will do the job for you. If you take f of x, so actually let me take this as x cubed. If you take f of x plus 1, so fx is x cubed plus 3x squared plus 2. If you take f of x plus 1, what is this? This is x, I am replacing x by x plus 1 here. So x plus 1 whole cubed plus 3 times x plus 1 whole squared plus 2. So now if you expand this and combine, so I'll quickly do this, and you can check it's correct. You will have x cubed term plus 3x squared, and there will be another 3x squared, that will be 6x squared, plus there will be a 3x here and a 6x here, so that will be 9x. There will be a 1, there will be a 3, there will be a 2, so that will be 6. Now p equal to 3 works, right? So that means 3 does not divide the leading coefficient, 3 divides 6, 3 divides 9, 3 divides 6, 9 does not divide 6. So we can conclude f of x plus 1 is irreducible, right? So f of x plus 1 is irreducible. What can you, because this is a polynomial to which Eisenstein criterion applies, and that we can say is irreducible, and I should actually say in Qx also in Zx, because it's a primitive polynomial, so it's also irreducible in Zx. But original question is for fx, and what can you say about fx? I claim that fx is also irreducible in Zx. Why? If not, we can write fx as some gx times hx. This is a polynomial identity. So let me just first do q for simplicity. It's a polynomial identity where g and h are positive degree polynomials, and every time you have a polynomial identity, we can formally replace the variable by any other expression. So fx plus 1 has to be gx plus 1 times hx plus 1, because both sides you are replacing by x. But this, if gx is positive degree, this implies degree of gx plus 1 is also positive degree, is also positive, because again if gx is x power 3, x power 2, g of x plus 1 will be also, there will be x squared term there, because x plus 1 whole squared will appear, and then that will give you x squared. So the degree of gx plus 1 is same as degree of gx, degree of hx plus 1 is degree of hx, and here you have written fx plus 1 as a product of two positive degree polynomials. This violates irreducibility of f of x plus 1. So fx plus 1 is irreducible by Eisenstein criterion. If fx is reducible, fx plus 1 is also reducible, violating the conclusion earlier. So fx is also irreducible. Once fx is irreducible in Qx, fx is primitive, so fx is also irreducible in Zx. Okay, because if it's primitive and it's irreducible in Qx, we proved already that it is irreducible in Zx. So the final example I will give for Eisenstein criterion, which is actually a very useful example, and it will come when we study fields and field extensions called cyclotomic field extensions, and this is the following. So let p be any prime integer, let p be a prime integer, let fx be the polynomial given by x power p minus 1 times x plus x power p minus 2 plus x power p minus 3 and so on, x squared plus x plus 1. So again my question is it irreducible over Qx? If so, it will be irreducible over Zx, but we can't use no prime works, right? Again, no prime works in the Eisenstein criterion because all the coefficients here are 1, so certainly no prime divides the coefficients. But again, the trick is to use what I have done in the previous example, but what I will do now is, if I multiply fx by x minus 1, what do I get? So I get x minus 1 plus times x power p minus 1 plus x power p minus 2 plus x squared plus x plus 1, and now if you multiply this out, what you get is simply x power p minus 1, because all the other terms will cancel out, right? There will be an x power p minus 1 plus x power p minus 1 minus x power p minus 1, and you will cancel all the terms except this. So what you will have is x minus 1 times fx is this, but then I set y is equal to x minus 1. So I am changing variables here. What do I get? I get y, this equation, so x minus 1 times fx equals x power p minus 1. So in this I am replacing x minus 1 by y. That means y times, if y is x minus 1, y plus 1 is x. So fx is fy plus 1. So y times fy plus 1 is x minus 1, or rather xy plus 1 power p minus 1, because x is y plus 1. So y times fy plus 1 is equal to y plus 1 power p minus 1. But what is this? This is y power p plus p y power p minus 1 plus p choose 2 y power p minus 2 all the way up to p y power py, right, plus 1 minus 1. So this until this is just y power 1 power y plus 1 power p. If you expand y plus 1 power p by using binomial theorem, this is what you get: yp plus p yp minus 1, p choose 2 yp minus 2, and so on, plus 1 at the end. So you cancel that 1 with this minus 1. What you end up with is y power p y power p minus 1, p choose 2 y power p minus 2 py. Okay, now this looks more promising, right? You can conclude that this is irreducible using, so let's call, this is f times y times fy plus 1 by Eisenstein criterion. What we need to claim is, and this I will leave as an exercise for you, this is a very easy exercise. P divides p choose I for all I from 1 up to p minus 1. Okay, so of course when you take I equal to 1, p choose I is just p, so p divides that. P also divides p choose 2, p choose 3, and so on. Here the important fact is that p is a prime. So the reason is you can write p choose I as, so this is by definition p factorial by I factorial times p minus I factorial, right? So suppose you cancel I factorial or p minus I factorial, you have p times p minus 1 up to p minus I plus 1 by I factorial, right? So I have cancelled p minus I factorial from numerator and denominator. So now if you look at this, I is strictly less than p. So p is not going to appear in the denominator, right? I factorial is 1 times, 2 times, 3 times up to I. So p does not appear in the denominator, whereas p appears in the numerator. So that means p divides this. So this is a quick hint, but I will let you finish the argument and show that p divides p choose I for all I. So y times fy plus 1 is irreducible in qx and zx by Eisenstein criterion, right? This is because p divides all the coefficients other than the leading coefficient. P divides this, p divides p choose 2, p divides p choose 3, p divides p, and p square does not divide the last coefficient. Okay, so actually, sorry, I should, this is not quite correct, so I should continue one more step. So what we have is y times fy plus 1 is equal to y power p y power p minus 1, p choose 2 y power p minus 2 plus py. Now I divide by y both sides, so I cancel y, divide by y. What I get is fy plus 1 is y power p minus 1 p y power p minus 2 p choose 2 y power p minus 3 p choose 2 y plus p. If I divide by the previous term is p choose 2 y squared, so that becomes p choose 2 y plus p. Now apply Eisenstein criterion. See, earlier we can't apply Eisenstein criterion because the leading coefficient, the constant term is 0. Now we can, to conclude that fy plus 1 is irreducible. But what is fy plus 1? Y plus 1 is just x, right? So remember, that was our change of variable. Y plus 1 is x. So Fy plus 1 is irreducible, so Fx is irreducible. Remember, Fy plus 1 is irreducible again in Zx, I can say. In Qx or Zx, it's irrelevant here. So this is because P divides all the coefficients here other than the first coefficient, which is 1, and P square does not divide the constant coefficient. So this Eisenstein criterion applies to this to conclude this is irreducible in Qx, but this is also primitive, so this is irreducible in Zx. So Fy plus 1 is irreducible in Zx, so Fx is irreducible in Zx because y plus 1 is equal to x. So in this video we looked at Eisenstein criterion, which is an extremely useful technique to prove irreducibility in Qx or in Zx, and we also looked at some examples. So this completes whatever I wanted to say in this course in ring theory. So in the next 1 or 2 videos I will do some problems on rings just to summarize whatever we have done, and then we will go to fields. Thank you.